Hello, everyone. Welcome to our brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, ask us any questions during the episode so we can get to them, as well as subscribe to get notifications of our future episodes to come. And also, if you're watching this offline, we do this every Tuesday at 5 p.m. Pacific, 8 p.m. Eastern. So with that out of the way, let's get to it. So I guess Tim, they recently announced the Nobel Prize in Physics for something relating to quantum entanglement. I guess like I guess the things I want to ask about are generally like what does that mean and like what's the significance of that? So how do you think we should dive into this? Like should we kind of take a step back and describe like high level like the concepts behind that went behind this or just cut to the punchline, state what they won the Nobel Prize and then work backwards?
Yeah, let me just have a one sentence punchline. I feel like all the media coverage and all the complicated stuff, it just kind of muddled the significance of it. And in some sense, the Nobel Prize was way overdue, right? The crux of it was just that they proved that quantum mechanics works. That's really the crux of it. And you can slice and dice entanglement, quantum information, Bell's inequality, blah blah blah. All this are just the foundational aspects of quantum physics. Like quantum physics requires it, and it's a little strange that we've studied many things that absolutely require quantum mechanics. Things like superfluids, semiconductors. You know how computer chips work, the expansion of the universe, and the logical structure of the universe. Many of these things are completely dependent on the fact that quantum physics work. But then we've never kind of directly say that, hey, well, these foundational aspects works. So this Nobel Prize was just exactly about the foundation of quantum physics, that the assumptions, the math, the basic stuff checks out. That's what the Nobel Prize was about.
I see. So actually, one question I have about that is like I thought quantum physics was all about probabilities, and we have classical probability theory. So like, what's the big deal about this? Like when you talk about foundations, what do you mean by that? And how's it different than classical probability theory?
That is the point, right? They showed. Sorry, I'm like not super expert on the topic of this, but yeah, that's my understanding. Like they essentially showed that quantum mechanical probability is different from classical probability in that you can't explain one with the other. Tim, correct me if I'm wrong.
Yeah, no, I think that's correct. I mean, like we have ordinary probability. Like for example, we see a lot of probabilistic things in the world. We flip a coin, we don't know if heads or tails, right? We roll a die, and it could be 1 out of 6 is roughly equal probability. And then some physicists go to the lab and check out these subatomic particles, and you see that, hey, the position of an electron, it's probabilistic, or something called like the spin, which is kind of like a quantum coin flip, right? Spin can return up or down, which is kind of like zeros and ones. And they also see that that's probabilistic. It's like flipping a coin. But of course, the natural question is, well, how is that different from actually flipping a coin, right? Like these subatomic particles. Maybe they're not different, right? But it turns out that they are different, right? The rules are different. But then, physics is an experimental science. We need to really tease that out, right? Like there's still doubters out there doubting quantum physics. So we gotta make sure that those doubters have no argument whatsoever.
Yeah, yeah. So actually, like, so you mentioned there's a difference between like classical probabilities, such as like rolling a dice, flipping a coin, and measuring subatomic particles. But like, how do you know that? Like, isn't it just that we could be missing information? And just like when classically when you flip a coin, if you knew every single thing about the coin, the initial conditions of how much force I applied to it, what orientation it was, I'd be able to predict exactly what it would land on. But it's because I don't have all that information, I need to resort to probabilistic models. So how's that different? Like,
Yeah, I think to do that, it's situational, right? Like in many
mm,
aspects, because look, ultimately the world is quantum mechanical. So some of the probability that we see, like flipping a coin, it is described by classical probability, and we also know that if we believe quantum physics is right, it also have to come from quantum physics in some way, one way or another, right? So it has to be situational. So we have to look at situations when when normal probability does not work, and these have to be very specific circumstances. I don't know, like Mikey, what do you think?
Yeah, I mean, I think probably most listeners have taken high school chemistry and have learned about the uncertainty principle, right? It's this idea that if you look at the fundamental laws of nature, there's a certain amount of uncertainty that you can never remove, right? You can't exactly predict everything the way Einstein wished we could in a deterministic universe. Um, and so that's like immediately when I heard that, it's like, oh, like, is that really true? Like, how do we know that? How do we know that there has to be this irreducible amount of uncertainty in the world? As Tim mentioned, with normal probability theory, the more information you have, the less uncertain things become. And so the uncertainty principle is kind of the statement that there's a limit to how much you can reduce the certainty by gaining knowledge.
Huh. So I guess like how do you sort of reconcile that? I'm still wondering with like quantum mechanics, like this irreducible uncertainty. There's the uncertainty principle, but that how do we know it's not like contrived and
Yeah, how can we show that it's really irreducible, right?
Yeah.
I guess that's what these guys got the Nobel Prize for.
Yeah, I guess that's the difficulty, right? Like you can't, like in order to prove it, you have to be exhaustive. Like quantum physics just postulate that hey, there's some irreducible uncertainty, and then of course physicists will be like, well, the doubters would just be like, well, maybe you didn't try hard enough, maybe your theory is not good enough, right? Like you can never satisfy fully what doubter says, because these are kind of like negative arguments. But yeah, geez, you just didn't try hard enough. It's just not good enough, right? So you can never exhaustively show that to deny these doubters that excuse. Be like, hey, I try as well as possible. So you can't do that. But it turns out that there are systems that are just so outrageous that you can just show that no matter really how well you try, it just doesn't make sense any other way. It turns out there are systems that people have observed that have these behaviors, and these are, and this is where entanglement comes in. These are entangled system has got these super duper strange behaviors, and that's why where we can say, hey, we try as hard as we can, and something's got to give.
Gotcha. So I guess before we delve into maybe what the systems are, we've mentioned the word entanglement, and we've mentioned it over several previous episodes, but for any listeners, can we define what entanglement is? Like, how can we think about it? I'll go, Mikey, pick on you.
I think it's kind of like interesting that like when we talk about entanglement before, we almost talked about it in like the opposite vein, right? Like we talk about two particles. Like there's a phenomenon that can happen in nature where you can take two particles, and it's possible for these two particles to be in a state where we call them entangled, like fully entangled or maximally entangled, meaning that if you look at one particle, that tells you everything you need to know about the other particle. So it's almost not a statement about certainty, uncertainty. It's almost a statement about certainty, right? Like I'm saying that if I have two objects and I show you one, you can be absolutely certain about all the properties of the other one, because these two particles are maximally entangled, meaning that all of their characteristics and properties are dependent on each other, which means that if you know one, you can infer all the properties and characteristics of the other. So it's kind of weird that like from this idea of like certainty through entanglement, we kind of derive this uncertainty principle.
Is that different than like perfect correlation, or is that exactly the same? Because correlation is a classical concept.
Yeah, it's like, well, correlation is also a quantum mechanical concept, but in real life, there's no such thing as perfect correlation, right? It's only with quantum mechanics that this kind of like theoretical idea of perfect correlation can actually even exist. Actually, even in quantum mechanics, it can't really, right?
No,
Because
I
that
think
would require two things that are not entangled with anything else, which
I
I
would
don't
say
know if that's what would happen.
it's a bit more perfect, right? It's so this is kind of a bit paradoxical, like Mikey was saying, right? Like there's uncertainty, but there are also systems that have give you more certainty, right? So I think classically, normally when you say something is correlated, um, you would argue that it's kind of correlated. I wouldn't maybe kind of by accident, right? Like imagine if two balls are correlated. Like let's say they have the same color. Or maybe the two balls just come from the same basket, right? And that's the reason why they correlated. But entanglement is a little different. Entanglement means that every single property of the particle, at least some subset of the particles, are 100% correlated. And let me give you an example. Like so for example, you can measure something like the spin, let's say, and these are completely random. Like if you just look at one of the entangled particle, like imagine I have two particles, one and two, they're entangled, right? Perfectly entangled. And for particle one, you can measure this thing called spin, which is kind of like a coin flip. So every time you look at it, it's 50-50 heads or tails, right? But then there are infinitely many ways for you to measure it, right? To some extent, there are infinitely many different random coin flips you can do, and they'll all be 50-50, 50-50. But the strange thing is, no matter how many times you do it, and let's say you do the same thing to the other coin, you find that those are exactly equal. The answer, even though individually they're random, when you compare them, they're exactly equal, right? And then this is really strange classically. So it's like imagining you have two balls that has infinitely number of colors, and all these colors are exactly the same, right? Even colors that you have never imagined before. Like that's what we're talking about. This is kind of like an infinite amount of correlation. That's the strange thing about this system.
So every single thing is perfectly correlated if you have two perfectly entangled particles. Am I understanding that correctly?
Yeah. And in some sense, the essence of the Nobel Prize is to think about this entangled system. Is this entangled system quantum mechanical, or is it not? Maybe they're just kind of two balls from the same basket. They're not entangled. That is the crux of the Nobel Prize. They prove that it is the former, that it is not possible that entangled particles are actually two balls from the same basket. They're not. They're just something.
The same ball, right? They can't be the same ball.
Right. Yeah. But in some sense, they're kind of the same ball. Like that's the strange thing about it. It's almost like what people say, like spooky action at a distance. It's almost like every time you measure something about particle one, that information just instantaneously translate to particle two, right? Like that's that's one way of some people putting it. I don't like that interpretation, but
no one likes that interpretation.
Yeah, no one likes that interpretation, but some people try to think of it that way.
Huh. Okay. So if entanglement is this perfect correlation at a quantum mechanical level, then like what went into proving that, as much as we can say at a high level?
Yeah.
Proving entanglement?
Yeah, or how did they win the Nobel Prize is just like my question. Like what did they do to win?
I want to know the answer to this as well.
I mean that's a fair question. If you look at all the scientists, I suppose we should have their names. So if you
don't have their name.
Yeah, I don't exactly.
Aspect, Clauser, and Zeilinger.
Zeilinger's the only one I know because he's on all the PBS shows.
Yeah. Alain Aspect, John F. Clausier, and Anton Zeilinger. Yeah, I think you have a mixed bag here. Some of them are like I think two of them are theorists. I forgot which two. Like they write quite a few papers just about sanity checking. It's almost like you're playing devil's advocate. Be like, hey, I want to show that these behave like classical probability as hard as possible. But then ultimately find that, hey, it's contradictory. Like that's what they're trying to do. Like a lot of them just come up with all these elaborate sanity check you can do, and see and then you see that quantum systems actually fail these sanity checks, and to show that it's not possible. Like so that's where a lot of those papers are about. And then I think there's an experimentalist, I don't know which one, that actually help.
Zeilinger is experimentalist.
Right, that actually help out carrying out these experiments, and they do indeed show that quantum system behave quantum mechanically as expected.
Huh. So is entanglement like the entire basis for this, or is there something in addition to entanglement that's like the basis for this?
Go, Tim.
Yeah, I mean, there is something special, and this is what's known as the Bell's inequality, right? And it sounds complicated, but really, it's a way to sanity check classical probability. It's to say that I don't care what classical probability you have. There's certain things about the system it has to satisfy, right? And it turns out that it doesn't, right? And we can give a few examples. Well, maybe just one.
Go for it.
Yeah.
Give me an example.
Yeah. So one example. So you not do that. We dig into what we call quantum information theory, right? Zeros and ones, basically bits, right? That's kind of the building block of these probability stuff, right? So the smallest system, the smallest system for you to show some kind of interesting behavior, it turns out requires 3 bits, right? 3 bits, 3 zeros and ones.
3 coins.
3 coins, right? Okay. So imagine you have 2 entangled particles, right? So they're entangled, they're perfectly correlated, and each particle we arm them with 3 coins, right? So each particle has kind of 3 coins that they can play with, or you can choose to play with the 3 coins of the particle, and then you can separate these particles really far away, like they can be on opposite sides of the galaxies, right? And then you can check that these 3 coins, whenever you flip them, doesn't matter how you flip them, they're always fair. It's always 50-50 if you flip them individually. And then they are perfectly correlated, right? So particle 1 could be an Andrometer, and let's say you choose to flip coin 1, you get heads. And then the other particle is in the Milky Way, our galaxy. You see that it's 1. And you can repeat this again and again. Let's say you have many of these pairs. You see that they're perfectly correlated. So born from this experimental setup, you can cook up some really interesting ways to choose the coin flip that is unexplainable in the conventional way.
So you're saying that this experiment involving 2 particles that are entangled with each other would not follow the rules from classical probability.
Yeah, exactly. Yeah. So
I see. I have a little bit of a slightly tangential question, that like if you have 2 particles that are perfectly entangled with each other, and then you measure one, and then you measure the other one, let's say they're on opposite sides of the galaxy, then those 2 particles get entangled with the measurement devices themselves that are measuring them. So how do they end up knowing that they give the same result?
Right. So in quantum physics, there's this weird thing that whenever you measure something, you kind of completely mess up the system itself, right? Fundamentally, measurement disrupt the system, right? So you're right that when you measure particle 1, you have disrupted that system, right? But it's not totally disrupted, that you can still measure the second particle. But after that measurement, this entangled particle pair is completely destroyed, right? You can't do multiple measurement, right? But then if the 2 physicists, let's say from different ends of the galaxy, come together and compare data, they'll find that, hey, for that one entangled pair, the result is exactly identical. So you gotta repeat this many times. You gotta shoot like millions and millions, maybe not millions, but hundreds and thousands of these entangled particles, and repeat it again and again to gather statistics for this to have a power. So yeah, so individual measurement doesn't tell you much, right? But then once you repeat it again and again, you notice something funky is going on.
Yeah. Okay, so actually I want to kind of go on like a meta level here. So we talked about there's a difference between classical probability and this and quantum mechanics, but yet the way you described it about repeatability is a notion of like classical probability saying that, oh, these two particles are most likely entangled with each other because you're comparing them, right? In a classical sense.
Well, we can cook up. I mean, in experiments, of course, you try to replicate the setup as much as you possibly can, right?
Mhm.
And you can do other sanity check to make sure that they have that behavior, right? Like, I mean, for example, you like every other particle you shoot out, you can try to see that they entangle. Like in some sense, you're right. Like you can never be sure that they're totally entangled because you don't know. Because once you measure them, they're destroyed, right? But then, of course, in a statistical aggregate, you can show that hey, maybe your method really does produce entangled particle, and sometimes it's quite reasonable. I think usually they do it with particle of light like photons, right? They
Mhm.
literally have what we call beam splitter that kind of split a particle into two. Like it's kind of like what because photons are kind of like amorphous. You can kind of do that. Then it's like
Mhm.
hey, you're creating two particles out of one, so kind of like you know kind of makes sense that they entangle, right? But in any case, you can kind of use other tests to ensure that your setup is legit before you go ahead and do this. And sometimes in science, you have to take that leap of faith to say that hey, like if I didn't muck up now, probably I wouldn't muck up 10 minutes from now, right? So
Yeah.
Gotcha.
Maybe it's worth mentioning that like this is like a lot of the veracity of this comes directly from experiment, right? So if you have like two particles or two coins, if you like, they're separated, millions of miles apart. Physicist one measures coin one. By measuring it, he entangles himself with it. He or she entangles himself with it, and uh, that entanglement causes physicist one's brain to
Chris,
recognize that as a heads. Um, then physicist one should bet, $1 billion
Mhm.
that when they communicate with physicist two, who's entangled themselves with particle two in such a way that they interpret it as what did I say, heads or tails?
Is
The
it?
opposite. Heads. Then, it's one of the things. It's the best bet, right? Like there's like when we talk about correlation, classical versus quantum, right? Classical correlation, we know that like high body mass index is correlated with heart attacks, right? But you're not going to bet $1 billion that someone with a high body mass index is going to have a heart attack. But you'd bet $1 billion that if physicist one measures heads, then physicist two will interpret their measurement as tails as well. And so there's just like so many experiments have been done. There's never been observed a violation of this. So it's
yeah,
just striking from an experimental standpoint.
yeah.
Uh, am I hearing a quantum casino idea, Mikey?
like yeah, I mean you can go deeper into the experimental setup because quantum physics does deal with the act of measurement. But for this discussion, I think it's okay to ignore it. Kind of just keep in mind the framework of just flipping coin. You're flipping coin and you're observing it, right? And then you look at the probability that comes out, and then you see that you can set up in such a way that some of them don't make sense, right?
Yeah. Yeah, yeah. I guess then, so kind of like tying this back, actually, I want to take a step back and ask like experimentally, like at a high level without going too in depth into it, like how would this work? Like you would like both people would measure it, like you have, let's say you have two particles, they're entangled with each other, and you like drag them off at like, a fairly large distance, some distance scale. And then experimenter one measures it, and then experimenter two also needs to measure it, right?
Yes,
And
yes.
can they measure at different times or like same time, or like what
It
is the
it actually does not matter what time you
Hmm.
measure it, as long as you
And
coordinate.
actually, there's no notion of same time if they're
Yeah, there is
separated by
not.
distance.
Yeah, yeah.
Ah,
Exactly, exactly. Yeah.
clever.
Yeah, so let's just go through the setup wholesale, right? So basically imagine you have some particle let's say a particle of light, you split it by a beam, so a beam split or whatever, so that the two particles are entangled, right? The two photons are totally entangled. So particle 1 reaches detector 1, particles 2 reaches detector 2. And let's say you arrange it in that everything is perfectly correlated. You can also arrange it so that they're perfectly anti-correlated, so heads becomes tails. But to keep it simple, let's say that they're totally correlated, right? Okay, so these two particles. So you set up a system. So you're creating many entangled pairs repeatedly, again and again and again and again, right? And then now let's say you set up 3 different coins, right? What that means is basically the device is able to measure spin in 3 different orientation. You can rotate around and think of it as flipping 3 different coins, right? Okay, and then let's say even before the experiment begin, they can kind of figure out which coin to flip, right? They can decide some protocol. Maybe they will choose randomly based on some other random number generator, whatever, some protocol, right? Okay. Mm-hmm. Okay, so the first thing they can check is that, hey, if I just pick any one of the coins and just flip it, individually it's always fair. This is a perfectly fair coin. Heads and tails 50-50. They can check it, right? They can shoot a million, maybe not a million, a few thousand entangled pairs and just do it.
Why not a million? Just say a million.
So sure, a million, right? A million, right? A million, and they'll be like, hey, all these coins are perfectly fair, 50-50. Okay? And now things get interesting when you look at 2 coins now. Because we know that they're perfectly correlated, then detector 1 can take a peek at coin 1, and detector 2 can take a peek at coin 2. Now let's think logically, like normally, let's say using normal probability. If I have 2 fair coins, right, that's heads or tails, what's the chance that the 2 coins will be equal if I flip 2 coins? It's also 50-50, right? Because it could be heads, tails. It could be heads, tails, heads, tail, heads, right? So the probability that they're equal is still 50-50, right? But it turns out that in this entangled pair experiment, you can set it up in such a way that the probability becomes a quarter, right? So 2 fair coins, when you flip them at the same time using the entangled pair, the probability is a quarter. This is observed, like you can set it up that way. And that cannot be explained by ordinary probability. And this is what we call a violation of Bell's inequality, because the expectation is that it should be a half, but we get a quarter. And there just is no way to get it. Like 2 fair coins, how can you get a quarter probability that they're equal? It's almost like they don't want to be equal to each other in some strange way, right?
Or it's like there's more stuff.
Yeah, it's like there's more stuff, right? But so that's one possible setup.
Okay, so to kind of summarize that at like a high level, there's an experiment you can set up with entangled particles such that, like, with this inequality called Bell's inequality that holds for classical probability theory, this experiment clearly shows there's a violation of inequality, which means you can't explain this using classical probability theory, and there's some quantum mechanical explanation for this, i.e. entanglement. Is that a fair statement?
Yeah, basically it seems like if you were to use classical probability, the way you argue is that the reason why they entangle is just because each particle has already grabbed 3 coins on the way out, and they've already been flipped as they travel far away. And it just so happened that they grabbed the same, coins in the same orientation as they were heading out, right? So that when we find them the same, well, it's just by chance, right? But if we do that, there's no way a fair coins will yield probability of a quarter. So the idea of quantum physics is that there was no coin for them to grab. Basically, these coins don't really exist until they were measured. I think that was the crux. It's telling you that the result of something, of measurement or of interactions, do not exist until they actually get measured or they're interacted. Like, that's the weird thing now.
So what you're saying is it's like different than the case if like let's say a more classical situation where let's say I had like two sets of balls, they were either like red or yellow, and I made it such that like I put two balls of the same color in two boxes and then gave you one of the boxes and then gave Mikey one of the boxes and you didn't know whether it was like red or yellow, but you knew that if you open your box and you see red, Mikey's would be red. But this is different because it's not determined ahead of time. This is just it just happens as soon as you measure on
Yeah,
both sides.
exactly. Yeah, it's almost
Mm.
like it's almost like things are. It's almost like the property of something doesn't exist yet until you decide that hey, I want to compare whether things are equal, and then the system kind of formulate a response and say that hey, I'm gonna tell you, what is the chance that they're equal as the measurement happens. And of course, if that were true, these probability are completely unconstrained, right? They don't need to be a half or a quarter. They can be something else, in fact, entirely. And that's what we see. Sort of quantum physics has this freedom to have more diverse kinds of probabilities that you wouldn't expect normally, that you wouldn't be able to explain normally, that it happens.
I see. And so actually kind of stopping on that point you just mentioned, is it fair to say that like measurement is an act of fact creation in some sense? Because until you measure, like there is, I don't want to say like there isn't anything, but there isn't like I don't know what word I'm looking for, but there's no property. It doesn't
Yeah.
really exist
I
until you
It's
act.
almost like, yeah, objects are not real. Relationships between the
yeah.
objects are the only real thing. Like the interactions between them,
Yeah.
between two objects, are what exists. Those
Yeah.
two objects don't have existence independently.
I would like to change the choice of words. I wouldn't say
Okay.
measurement. I would say interaction is what makes those things real. Like because sometimes people think measurement, oh, somehow that has to do with consciousness because we're thinking about measuring and knowing about
Mm.
something. No, 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 no. It's about interactions because measurement requires interaction. So the currency of quantum information is actually interactions. Interactions causes a property to be defined, right?
Uh,
Yeah, Sahil, if I never interact with you, then we don't live in the same universe. It's like literally what it is. It's like, I mean, we
uh,
are interacting because, the airwaves I breathe are eventually interacting with particles, interact with particles through a game of phone that, ends up affecting you in some way to the butterfly effect. But if literally, if you hypothesize that there's zero interaction between us, we don't exist in the same reality.
So is it fair to say if there was like no entanglement, like zero between anything, that all like particles, or I don't know if they would be even particles, but all these like I guess like entities or whatever you want to call them would be in different universes? Or would it even not even make sense?
Different realities almost.
Yeah, I think that's fair. Like entanglement, it's like this. Yeah, it's like this game of telephone. It's the currency of this game of telephone. When things entangle, they're able to play this game of telephone to communicate and to realize a property, basically, to say that hey, guess what? My coin is up. My color is green. It's through these interactions, right? And then this game of telephone kind of perpetuate itself to everything in the universe, and in fact, this is how we perceive the world, and that really is the strangest thing, I think.
That's what it means to participate in our universe, is to participate in this bath of interactions.
Wow. Wow. All right, so we are at time. Before we head out, is there anything you want to leave our audience with? Mikey, I'll let you go first since you look very able and willing.
Okay, I mean, like honestly, okay, just full disclosure, when I first read about this Nobel Prize, it was kind of a head scratcher, right? Because like the things they show were kind of things that people already assumed, but they kind of just like really showed them. Um, and I guess now after this discussion, I actually have a bit more of an appreciation for this because it's not something that's really hammered down in grad school, exactly because of the fact that it's kind of something that people always already assume anyways. Um, but I guess it's cool.
yeah. I would say this thing about entanglement and quantum physics, it's a bit of a dichotomy. Like if you talk to physicists, like Mikey, me, and probably Sahil, a bit of you, Sahil, we just kind of take for granted that quantum physics is true. Like we never question it, right? It's just like, oh, okay, there's entanglement, the world is kind of strange, blah blah blah, right? Okay, but I think this Nobel Prize was kind of a whole, like a message to the wider audience to really tell the public that, dude, like the world is quantum mechanical. Like this, it's real, it's legit. Like you, for all you doubters out there, you can't deny it. I mean, which is fair. So it is like really late, I would say, because we like we've proved that quantum physics work way before. But it's never too late to recognize some of these achievements, to really like kind of bring this to bring the quantum physics up, to kind of showcase its importance in the world, to kind of get people to appreciate its complexity. I would say that's a fair Nobel Prize.
Ah, all right then. Well, on that note, I want to thank you for joining us, and we'll see you all next week.
All right, see you all.
Yeah.
Bye.
Bye.
Bye bye.